Hello, and this is a pendulum quiz. So to start off, I'm going to swing a pendulum as an example. So this is our pendulum swinging, and as you can see, it swings back and forth left to right. So this diagram here is a free body diagram of our pendulum swinging. This string, this white string is a tension, which is right here on the top. And then we have here, this black dot is a pendulum, or in this case, a quarter. So we have here central angle theta. Now, if we want to be more specific on the FBD free body diagram, we could draw a right angle. And here's our central angle, theta. And adjacent to theta is cosine. So cosine is right here, and then the opposite would be sine right here. And mg would be the weight of the quarter or the pendulum, as seen here. So we have tension, central angle theta, cosine theta, and sine theta, and mg, which is a weight. But here we have Fr. Fr represents the restoring force. So as I swing this pendulum back and forth, as soon as it stops swinging, that's its restoring force. So Fr is our restoring force. The equation is Fr is equal to negative mg sine theta. The restoring force is what brings the pendulum back to the center, to the equilibrium position. So in this case, this would be the equilibrium position, being straight, not moving back and forth. So from here, our equation, restoring force, we can apply the small angle approximation, which says sine theta is approximately theta only if theta is small. So to give an example, we'll put our calculators on radian mode. We plug in sine 0.1 is equal to 0.0998. Sine 0.7 is equal to 0.644. And sine 1 is equal to 0.841. As you can see from these values that we obtained, none of these values are 1. In fact, they're less than 1. And because of this, these values show that theta is small. And because of this, sine theta becomes theta because theta is small. To give a reference, a unit circle that has a 360-degree angle, a degree of one degree difference will hardly make any change. It will be hardly noticeable to change the graph by 1 degree in a unit circle. So our restoring force equation originally was restoring force is equal to negative mg sine theta, and now becomes negative mg theta, negative mg theta. And so you might notice you have this negative value before the m, which is negative mg. And the reason why it is negative is because it is always opposite direction of the displacement vector. So for instance, in this pendulum is moving back and forth left to right. If I swing to the right, the restoring force would be going to the left. If I swing to the left, the restoring force would be going to the right. And that's why it's always opposite of the direction of the displacement vector. That's why it's a negative. So this is our equation now. Restoring force is equal to negative mg theta. So looking at these two circles right here, we have a circle. S is the arc length, theta is central angle, and r is radius. That's for a circle. Well, as you can see, this pendulum is swinging. I'm trying to replicate it as this graph right here. This circle is swinging back and forth left to right. You can see that you still have a central angle, and you have x, which is the distance that the pendulum moves. And then you have the L, which is actual length of the string of the pendulum. And this is our pendulum, just to make it easier to imagine. So these values is S is equal to theta r. We replace these variables with x. X is equal to theta L. Or displacement of the pendulum is equal to theta times the length of the pendulum. So here is our equation. Here's our formula. X is equal to theta L. But we want to find only theta, so manipulate it. And we do that by dividing by L on both sides. So we get theta is equal to x over L, or displacement of the pendulum divided by the length of the pendulum. So our equation now goes from negative mg theta to now negative mg x over L. So focusing on the left side, we have Fr, which is Hooke's law. Hooke's law says restoring force is equal to the spring constant times the extension of the spring. So only focusing on this left side Fr, FR now becomes negative K times X. So it goes, plugging in, it goes negative KX is equal to negative mg times X over L. So we have an X on both sides, cancel them out, and we're left with K is equal to mg over L. So since you have two negatives on both sides, they both become a positive. Negative makes a positive. So it's now K is equal to mg over L. So remember this equation. Remember this equation right here. So now here, starting from scratch, we're going to find the equation for a period. So as this pendulum swings left to right, or L and R, we see that it has a displacement and the amplitude. Amplitude is the distance that the pendulum moved. So this pendulum moves at a speed, right? So our equation for speed is velocity is equal to distance over time, d over t. But if I swing this pendulum with enough force, you'll see that it swings in a circle. It'll swing in a circle if I apply enough force without the pendulum flying off my fingers. So we can see that the distance is actually a circle, or the circumference of a circle, which is now 2 pi r divided by time. So time is a period for one oscillation, for one oscillation like this. So d is now replaced with 2 pi r, and now we have t for time for revolution. But since here the radius in this case would actually be a, the amplitude, which is the distance moved from the pendulum. So now it'll be 2 pi amplitude divided by t, which is our velocity. But we want to find t, we want to get t by itself, so we're going to have to do some manipulation. So multiply by t on both sides. On this equation, we get Vt is equal to 2 pi amplitude. And we want to get t by itself, so we want to divide by v on both sides like this, as shown. And we end up getting t time is equal to 2 pi amplitude divided by v. So applying the velocity, the max velocity formula, or similar to angular frequency, k is the spring constant, m is the mass of oscillating body, and a is amplitude. So here's our equation of the max velocity. We want to multiply k and m by the reciprocal, which is square root m over k, and then we get v square root m over k is equal to amplitude, or 1 is equal to 1. Same thing. These, even though they look different, they're the same values. So from this equation, t is equal to 2 pi amplitude over v. We want to replace a with v mk. So here's our equation. T is equal to 2 pi over v times amplitude. But now becomes t is equal to 2 pi over v times v square root m over k. And as you can see, we have two m's on both sides. So cancel out the v's on both sides. And now we get t is equal to 2 pi square root m over k. And this is our period of a spring equation, where t is the time, m is the mass of oscillating body, and k is the spring constant. So here's our period of a spring equation. The same thing right here. But you see here the k that we got here was k is equal to mg over L. K was equal to mg over L. But if we were to multiply m divided by mg divided by L, it wouldn't look right. So we're going to multiply by the reciprocal of k, which is 1 over k. And it'll be 1 over k is equal to L over mg. So it'll be 2 pi m over 1 times 1 over k, which will be L over mg. So it'll be 2 pi square root m over 1 times L over mg. We have the m on both sides, cancel them out, and we're left with t is equal to 2 pi square root L over g, which is a simple pendulum equation. So now that we have a simple pendulum equation, we want to solve for L, find the length of the pendulum. So starting from the simple pendulum equation, we're going to square both sides. So it's going to be 2 squared is equal to 4 pi squared times Lg. So as you know, squaring the root, to get rid of square root, we square it. So it's going to be Lg now. So we want to get L by itself, and it's L divided by G. It's not by itself. So the way to get rid of G is to multiply it by G on both sides. Now we're left with GT squared is equal to 4 pi squared times L. But L is not by itself. You have the 4 pi squared attached to it. So divide by 4 pi squared on both sides, and we get L by itself. L by itself is equal to gt squared divided by 4 pi squared, or length is equal to gt squared divided by 4 pi squared. And so the pendulum question asks us, what is the length of the pendulum that has a period of 1 second? Well, we're going to use this formula that we obtained right now. L is equal to time squared times gravity divided by 4 pi squared. And all these are constants except for t. T is given to us in the form of 1 second. So all we're going to do is plug in the variables. We get 1 second squared times 9.81 meters second squared divided by 4 pi squared. And we get 0.248 meters, or length is equal to 2.48 meters in order for a pendulum to have a period of 1 second. And so thank you for watching this pendulum quiz, and I hope you enjoy.